So now, this video discusses about the summary analysis on fluid mechanics. Where I will be looking at the concept of the fluids, what are the fluids, we'll be looking at what are the fluids, like that. We'll also be talking about actually properties of fluids. What are the properties of fluids? We'll be looking at the properties of fluids and also be looking at the concept of the density. So be looking at what we get as the density, that is in terms of the formula. We'll be looking at that. And also be looking at the concept of the pressure. Now in this case, the pressure that will be looked at will be the pressure in solids, and also be looking at the pressure due to the gases. So pressure due to the gases, and also be looking at the concept of the atmospheric pressure. So also be looking at what we get as the atmospheric pressure and some of the factors. So atmospheric pressure and the factors behind. So atmospheric pressure, that is you should have to understand about that one. But in case you need the detailed structure about the concept of the fluid mechanics, you just have to go through my video playlist where you have the detailed structure about the concept of the fluid mechanics. But for the sake of interest, this video just want to express the summary analysis about the fluid mechanics. And also be talking about the pressure of the liquid at least. So be looking at the pressure of the liquid at least. Pressure of liquid at least. Should be fluids at least, but it should be the liquids at least. The pressure of liquids at least. We'll be looking about all these things in a summary context. And I'll also be looking at what we call as the Pascal's principle. So we'll be looking at what is Pascal's principle all about. So we'll be looking at what we call as the Pascal's principle and some of the things or the principles behind. And from there I'll also be looking at what we call as the Archimedes principle. And this is a very interesting actually a topic to think about, and much as far as physics is concerned. So Archimedes principle. So we'll be looking at what is Archimedes principle at the end of the day. Then from there we'll be looking at what we call as the fluid dynamics, where we'll be looking at the continuity. What is continuity? We'll be looking at what is continuity. That is the continuity formula. We'll be able to understand what is continuity formula all about. But for the sake of the detailed structure about the concepts behind, you just have to refer to the actually full video discussed about these concepts in details. But in this case, this is just for the sake of the actually a detailed, that is for the sake of the summary. So we'll be talking about the continuity formula, and we'll also be talking about Bernoulli's equation. So Bernoulli's equation. So we'll be looking at what we call as the Bernoulli's equation. And by the way, all these concepts, talks about the fluid mechanics. I should say actually a continuity equation and the Bernoulli's equation is basically used on the flow of the fluids. So we'll be looking about all these things in actually details. That is in summary, but in the detailed structure, you just have to refer to my video playlist. Just have to look at the concepts in details through that video. But now we'll just have to express the actually a summary analysis about the actually these things. So keep that in mind. So we understand that the physics is said to be the study of the fundamental laws of nature, and one of the components of physics is what we call as the matter. So physics studies about the matter, and we have 3 states of matter. So if we say matter is anything that occupies space and has a mass, so we have 3 states of matter. We have solids, we have solids, we have liquids, we have what we call as the gases. So all these are the examples of matter. It should be 3 states of matter. We have solids, liquids, as well as the gases. What are the typical examples of solids? We can have, let's say, a desk. That is a typical example. We can have a desk, and I can have, let's say, a stone. This is, we can have, let's say, ice. All these are the examples of actually solids, and what you can mention about. And we have the examples of liquids, the likes of, let's say, water. This is the liquid. We have the likes of, let's say, ethanol. This is a liquid. And we have several examples of liquids that we come across with. We have the likes of gases. We have oxygen gas. So we have the oxygen gas. This is a part of the example of gases. And of course we have several examples of gases that you can come across with, like that. Now if we say fluids, what are the fluids? Now if we say a fluids, these are the actual substances that can flow. So we call them as substances that can flow. Substances that can flow, we call them as fluids. Substances that can flow, we call them as the fluids. And what are these substances? So we have gases as well as actually liquids. So gases and liquids are classified as the fluids. They are the substances that has an ability to flow. So if we say fluids, these are the substances that can actually flow. We call them as fluids. So how about the density? Now if we say a density, and it is symbolized as lowercase p. So a density is symbolized as the lowercase p, and it is defined as the ratio of mass of an object per unit volume. So this is what we call as the density, and the mass has to be in kgs, and the volume has to be in meter cube, by the way. So this is the SI unit for actual density, which is given as the ratio of the mass per unit volume. That is what we call as the density. And of course different substances has got different densities, and if we have the mass and the volume, we can be able to have the density in that way, and of which the volume can be the volume of, let's say, can be the volume of which this volume can be the volume of an object which has the definite shape, of which the formula for the volume is given as the area times the height of an object. And for the sake of interest, that is the formula for the volume for an object, for the definite object, the object which has the definite shape, the shapes like this. This is the definite shape, of which the volume is given as the cross-section area cross-section area of this cross-section part, and the times the height, which is this. You can be able to have the volume in case we have an interest into that one. But anyway, this is the formula for the density for the sake of interest. So it is given as the mass over volume. That is, so different substances has the different actually densities because of difference, because of the different in masses and also the volume occupied as well. So keep that in mind. And for the sake of interest, let's say if we have, this is a container, let's say a cuboid, and it contains the gassy particles like that. Let's say it contains the gassy particles, and let's say the container is measured. Let's say it is given as 2 meter, let's say 2 meters. Also this is 2 meters. Let's say we know the mass of the actual gases given as that. Now how can we have the volume of the container? So the volume will be obtained using the formula, which is a cross-section area times the height. And sometimes we can have even that of, let's say, a cylindrical container. You should also be able to understand how we can have the volume of such shapes. But the principle behind says that the density, which is symbolized as lowercase p, can be calculated using the formula mass divided by the volume. So this is the formula. And the SI unit, it is given as kg actually per cubic meter. So just have to get that. And also concept of the pressure. So if we say a pressure, this is the force exerted per unit area. That is what we call as the pressure. And that is given as pressure P, which is equal to the force divided by the area. Now the point of interest is that if we have, let's say, an object, let's say if we have an object which has been pressed on a level ground, it can be on a desk or whatever, but on some level grounds, and this object is exerting pressure on the ground, and let's say the surface area in which the object is in contact with the ground, it is given as A. Then we say the object is exerting pressure on the surface, which is given as pressure is equal to force divided by the area. This is how the pressure has to be, and basically this is the formula for the pressure in solids. And the surface area can either be, a rectangular surface of which the area has to also vary. You can also have the, circular surface. It means the area also be calculated in a different way. But that's how you have to understand about the pressure. And the pressure is given in Newton meter square. It can also be given in Pascal. It should be that. But all these are the basic units for pressure. And they can also be given in millimeter mercury. So pressure can also be given in millimeter mercury. So keep that in mind. So that is about the pressure in solids. Now, let's be talking about the air pressure, atmospheric pressure. So what is the atmospheric pressure? So atmospheric pressure. So what is the atmospheric pressure? Now, if we say atmospheric pressure, this is the pressure in which the air particles in the atmosphere exert on the Earth's surface. That is what we call as the air pressure. And basically, that is atmospheric pressure. That is the pressure in which the masses of air particles in the atmosphere exist on the Earth's surface. And basically it is symbolized as BATM, that is atmospheric pressure. And basically it is a constant which is given, it is a constant which is given as 1.01 times 10 to the power 5 Newton meter square. It is a constant, and it can also be given in Pascal. That is the same as having it as 101 kilopascal. So this is what equates as the atmospheric pressure, and of course it depends on different actually locations. So we have several factors that affect atmospheric pressure, although it is a constant, but it depends on some factors. So you may have some factors where atmospheric pressure can be more than this or can be less than this. So it depends on the several factors. So factors that affect atmospheric pressure, we have the temperature, and we have the altitude, and we have what we call as the wind speed. We also have what we call as the wind speed, and we have the likes of gravitation force. We have the earth rotation, and also the humidity as well. All these are the factors that affect atmospheric pressure in a given location. But atmospheric pressure is a constant, and it is defined as the air pressure. This is the pressure in which the air particles, or in which the air in the atmosphere exist on the Earth's surface. That is what we call as the atmospheric pressure. Now, the concept of the pressure in liquids at rest. So what you have to understand is that liquids has what we call as the weak intermolecular forces. Liquids has what we call as the weaker intermolecular forces. Therefore, liquids do not possess the definite shape, and the shape that they takes, it is the shape of their container. So hence it is something which is very difficult to have the pressure of liquids using the formula force over area. Instead, if we have a typical liquid, its pressure varies with actually height. Let's say if we have, this is a liquid like that. It is in a container, something like that. And let's say this is the case. Let's say this is the case. We have, this is the liquid, sort of. Now, as we go down towards the bottom of the container, the pressure of the liquids increases. So pressure at this point is more than the pressure at this point. Is more than the pressure at this point. By the way, the pressure of the liquids increases as we go down, increases with the depth. That's the principle behind. So which means if we can have, let's say, the pressure at the point Y is less than the pressure at X, less than the pressure at C, less than the pressure at B, and also less than the pressure at A. So the point that is with the highest pressure, it is point A, because it is at a great height. A point A, it is at what we call as the great height. Actually, it is at the point. Actually, a point A, it is a point A has a larger depth. So it has the larger depth. Hence, it is the point that is experiencing the greater actually pressure than the least. So in other words, the pressure in liquids increases, that is the pressure for the liquids at least increases with the depth. So keep that in mind. So what is that one? Now the pressure in liquids, it is given as the density of a liquid times the gravity, actually times acceleration due to the gravity and times the height. As you can see here, the pressure increases with actually height, where the density and the acceleration due to the gravity are constant, and the density it is for a particular actually a liquid. So take note of that. And also let's have the principle of the Pascal. What is the Pascal's principle? Now, a Pascal principle, this is the principle that is based on the liquid in a closed system. So what is that? If we have, let's say, this is the closed system. Let's say this is the closed system, like that. Let's say we have, the liquid in the system. Let's say that is the case. You know, since the system is closed, you know, the pressure that can be exerted here will be equally distributed. It also be the same pressure here. It also be the same pressure here. It also be the same pressure here. It also be same pressure here. That is according to the Pascal's principle. You know, there is an equal transmission of pressure. You know, there is an equal transmission of a pressure in a liquids which is across the system. That is according to the Pascal's principle. And what is that kind of liquid? The liquid should be actually incompressible fluid. In other words, should be the one kind of a fluid, not the mixture of fluids, but should be a liquid of the one kind. If it is a water, should be the water only in the system. If it is an ethanol, should be the only ethanol in the system. But that is according to the Pascal's principle. And basically it is used in the hydraulic lifters. Let's say we have the system. Let's say this is a hydraulic lifter. Let's say this is the case, like that. Let's say we have, this is a piston. And let's say this is a liquid in the system, and the liquid is incompressible. That is the liquid of the same kind. In other words, the liquid which is not mixed with another liquid of another kind. And let's say we have, let's say, a car somewhere here. This is a typical, you know, this is a typical system of the hydraulic lifters. Let's say that is the case. So Pascal's principle can be used in hydraulic lifters, where we can be able to, it can be able to lift up the very heavy objects. Let's say this is the piston that is exerting pressure, that is exerting force down, given as F1. And let's say this is the surface area of the piston given as A1. And let's say the force that is being exerted here, it is exerting the pressure in the liquid. You know, that is pressure given as P1. And for that case, since this is a closed system, and since this is the closed system, there is an equal transmission of the pressure. That is to say, the pressure exerted here, it also be the pressure that will be felt here. Hence, there will be the pressure, which is pressure 2, on this object. And this object will be easily lifted up. But now since that pressure is the same, the force that is to be exerted here will be more than the force that is being exerted here, and I'll call it as force that will act upwards, that is F2. And let's say the surface area is given as A2. According to the Pascal's principle, it states that there is an equal transmission of the pressure in incompressible fluid. So which means the pressure 1 is the same as the pressure 2. So what is the pressure 1? The pressure 1 is given as F1 over A1, which should be equal to F2 over actually A2. This is what we call as the Pascal's principle, of which we can be able to have a force 1 if we have area 1, F2 as well as the area 2. So that is what we call as the Pascal's principle. And in terms of let's say how much the piston has to be pressed down in terms of the distance, I'll call it as D1 with respect to the area of the piston, and also how much this object has to be raised up. And let's say I should have it as in terms of, let's say, distance given as 2 upon this force being applied here, and also with respect to the surface area. Then the Pascal's principle can also be expressed as area 1 D1 is equal to area 2 D2. This is also what we get as the Pascal's principle on the distance actually basis. So keep that in mind. That is what we get as the Pascal's principle, and only it is applied on the actually incompressible fluid. And also let's be talking about the Archimedes principle. So what is an Archimedes principle? What is an Archimedes principle? So according to the principles behind the Archimedes principle, let's say if we have a container, let's say this is a typical container. Let's say that is the case, and the container contains some actually liquids. Let's say that is the case. Let's say the liquids is let's say about in a height 1. I'll call it as that. Let's say the liquids is about some heights here given as H1. Now if we press in an object, let's say we have pressed an object inside, what will happen is that the level of the liquids will increase. And let's say for the sake of interest, the liquid level can reach at this point. Let's say the liquid's level can be at this point. Let's say now this is an object that is being pressed inside. Now the liquid level will be at this point. Let's say given as H2. As you can see, there is a difference in the heights. There is a difference in the levels of the liquid. So the liquid which is this change in liquid, this liquid which has been increased in the levels is said to be the displaced liquid or displaced fluid. This is what we call it as the displaced fluid. We call it as the displaced, and this is basically happens in our everydays, whereby if we have an object being pressed in a liquid and the liquid level goes up because the space that has been occupied by the object, actually because this object occupies some space, that is end up displacing the fluid in that container. So what is the actual Archimedes principle? So according to the principles behind the Archimedes principle, it states that if an object is partially or fully immersed in a fluid, it experiences upthrust force. It experiences what we call as an upthrust force. So for that case, this object will experience the upthrust force, the force that will act upwards. That is to say, that is to be called as Fu. That is the upthrust force, and that particular upthrust force will be equal to the weight of the displaced fluid. That is the weight of the displaced fluid. In other words, as this object has been put in this liquid, this object will be actually sinking down. As it is sinking down, as it will be sinking down, some liquids will be dispersed, which is of this amount. And it reaches a point whereby the object won't be sinking forever. It will stop. And why will it be stopping? Because at each and every point in which the object is sinking down, there is an upthrust force due to that particular dispersed actual liquids. If that is the case, that force is said to be the upthrust force. And that upthrust force will be equal to the weight of the displaced fluid. So keep that in mind. So upthrust force will be the same as the displaced fluid. And another name of the upthrust force is said to be the buoyancy forces. That will be given as FB. Upthrust force is the same as the buoyancy forces. That is the same as Fu. That will be given as now the density of the fluid, times acceleration due to the gravity times the volume. So which means the weight, which means the weight of the dispersed fluid will be given as using this formula, where this is the density of the fluid dispersed. So which means FB, which is the buoyant force, which is the same as the upthrust force, is the same as the weight of the dispersed fluid. So what is in that dispersed fluid? We have it as density of the fluid, and it times acceleration due to the gravity, and times the volume of the fluid. So this is the formula that is used to find the weight of the dispersed fluid. So that is what we call as the Archimedes principle. And of course you may tend to wonder, why should we say the weight of the fluid should be expressed using this formula? By the way, the weight is the same as the force, of which force is given as the mass times acceleration due to the gravity. But what is mass? Using the density formula, mass is given as density times the volume. Hence force is given as density times volume times acceleration due to the gravity. That's why we have the formula for the dispersed fluid being given as that. That is in case you may tend to wonder what's going on there. So I just have to use the Newton's second law of motion and on the force itself. So this is what we call as the Archimedes principle, which states that if an object is partially or wholly immersed in a fluid, it experiences the upthrust force, which is said to be the buoyant force, and which is the same as the weight of the dispersed fluid. So which means the object has to float in order, or has to float in liquids, when the upthrust force is the same as the dispersed fluid. But now what happens if it is to fully immersed in a liquid up to the bottom level? So what do you think is the reason? So I want to see the response in the comment section below. That is in case if you have an interest to have the detailed look about that one. And now let's be talking about the liquid's flow. Should be the fluid's flow. I should say the flow of the fluids. Now to say it like that, the flow of the fluids. The flow of the fluids. The flow of the fluids. So let's have a look at the flow of the fluids. So on the flow of the fluids, we have two actually concepts. We have what we call it as the continuity. We have what we call it as the continuity equation. So on the continuity equation, you know, this one obeys the principle of mass conservation. Obeys the principle of mass conservation. Mass conservation. That is what we call as the continuity. And we have the another concept of Bernoulli's equation. Now on the Bernoulli's equation, you know, this equation follows the principle of energy conservation. Energy conservation. So that is about the Bernoulli's equation. It follows the principle of the energy conservation. So let's start with the continuity equation. So what is that? Of course, if you need the detailed structure about these things, just have to refer to my video playlist to come across with this. And I'll also post the links in the comment section below where you access them. But this is for the sake of the actually a typical summary analysis about the fluid mechanics. You know, let's say we have a system of the pipe. Let's say this is a pipe like that, and let's say we have it is being, you know, divided like this. So it means that this pipe has two sections. Let's say this is section A. Let's say this is section 1 and this is section 2. And let's say this actual section has the cross-section area given as A1. And this section has this cross-section area given as A2. Let's say that is the case. And we have the flow of a fluid in this pipe. And let's say the fluid is moving at a speed of quite as V1, like that. And by the way, towards this direction, as it is here. And now, you should have to understand that the pressure in which this liquid experiences in this pipe will be less than the pressure in which this liquid will experience in this pipe. So should be that. And let's say the fluid in this actual pipe will now have the new speed given as V2 towards this direction, that is. Now in this case, this section of the pipe will experience the pressure occurred as P1. In this section, we experience the pressure given as P2. Let's say that is the case. Now, if the fluid that is flowing in this pipe is a compressible fluid, a fluid that is you can be able to compress, then the continuity equation will be given as P1 should be V1 A1, which is equal to pressure 2, area 2, velocity 2. That is assuming there is no loss of the fluid at each and every point. So which means the mass in this section, mass 1 will be the same as the mass of the fluid in this section, mass 2. So assuming that there is actually a mass conservation It means the fluid that is to flow in this actual section also be the same as the one to be from that section. Only that the speed will differ, and also pressure also differ. That is for compressible fluid. So this formula for the continuity is for the compressible fluid. But now if it is incompressible fluid, pressure is the same. Hence volume actually is, hence speed 1, area 1 is equal speed 2, area 2. So this is the formula or the continuity equation that is for the incompressible fluid. So keep that in mind. And let's finish with the Bernoulli's equation. Let's finish with what we call as the Bernoulli's equation. So what is Bernoulli's equation? Let's say we have the pipe. Let's say this is the pipe. Let's say this is a pipe, and that contains the flow of the liquids. And let's say we have the liquid flow towards this direction with a speed given as V1. And let's say the pressure is given as P1. Let's say this is section 1. And this is the section 2 of the pipe, where we have the pressure given as P2. And the fluid is flowing towards this direction with a speed given as equal as V2. Let's say that is the case. Now, provided the pipe is at a constant height, that is, provided the pipe is at a constant height, let's say it is being horizontally pressed, let's say that is the case, and let's say there is energy conservation. The energy in this section is the same as the energy in this section. Then the Bernoulli's equation states that Bernoulli's equation will be given as P1 plus half density. So density times speed 1, and that is square will be equal to now pressure 2 plus half actually density times volume actually times speed 2 square. So this is what equates as the Bernoulli's equation at a constant height. So that is, if the work or the energy in a section 1 is the same as the energy in section 2, then this is what equates as the Bernoulli's equation. And that is if the pipe is at a constant height. So this is the work or the energy. This is for energy 1, and is equal to the energy 2. So take note of that. And what if there is a change in height? Let's say we have the pipe that is placed like that. Let's say this is the case. That is now on the changing height. So if that is the case, let's say we have, this is the section of, let's say, Y1, and let's say this is the section of Y2. That is if we will regard this is the height like this, where this is Y1 and this is the Y2. Let's say that is the case. So which means the height in which the pipe is changing should be, let's say this is the height given as that. Anyway, that is for the sake of interest. But this is a position Y1 and this is the position Y2, and this is the height. And let's say the cross-section area is constant. It is the same. So since the cross-section area is actually constant, it means the fluid flow will have the same speed. Let's say the speed here will also be the same speed at this point. And let's say this is section 1 and this is section 2. Let's say that is the case. And this is the height. That is from here up to here. Let's say this is given as the height. And let's say a pressure at this point, let's say should be given as P1. And the pressure at this point should be given as, let's go it as P2. Now, assuming that there is no loss of energy from here up to here, then the Bernoulli's equation will be actually expressed as P1 plus, and that is a density of the fluid, acceleration due to gravity, position 1 is equal to P2, and the plus, that one of gravitation, acceleration due to actually a density, acceleration due to gravity, and times the position 2. So this is what we call as the Bernoulli's equation on the changing height. So that's how you should have to understand about the summary analysis about the fluid mechanics. So here's the question for you. What are the applications of the Bernoulli's equation in real life situations? So I want to see the responses in the comment section below and after that. But in case you are in need of the detailed instruction about the fluid mechanics, just have to refer to my video praise to come across all these things. And else, I also post the link in the comment section below for you to have the better way. Thank you.